it is late.
Oh,
You are
yeah.
staring at your IDE. The glow of the monitor is pretty much the only light in the room. And you're trying to wrangle this incredibly sophisticated neural network into doing exactly what you want.
Oh, yeah. We have all been there, just staring at the screen.
Right. You are dealing with these matrices of billions of parameters. It's
Yeah.
calculating high-dimensional geometry at, like, lightning speed. I mean, it really is the pinnacle of human engineering.
It absolutely is.
And yet, to get this cutting-edge machine to perform at its best, the secret weapon is treating it like a third grader taking a math test.
Yeah, it sounds ridiculous when you put it like that.
It is ridiculous. Why does typing, show your work suddenly make a billion-parameter model act like a genius instead of just this hallucinating mess?
Well, it really forces us to confront how we actually interact with these architectures. We build these massive, mathematically profound systems, but the trigger to unlock their complex reasoning isn't like a low-level hyperparameter tweak.
Right, you aren't adjusting the learning rate.
Exactly. It's a syntactic hack. And the source material we are looking at today for this deep dive, the notes from the prompt engineering module, it dives straight into this.
Yeah, the concept of chain of thought prompting, or COT.
Right. And to understand the mechanics of why COT fundamentally alters the model's capabilities, we really have to look at the baseline method for triggering it, the basic approach.
Zero-shot COT.
Yeah, zero-shot COT, where you literally just append a single phrase to your prompt. You just type, let's think step by step.
Okay, wait, I have to push back on the physics of this right out of the gate.
Sure, go for it.
Because as a software engineer, the neural network is mathematically identical before and after I type, let's think step by step.
Right, yes. The weights are completely frozen at inference.
Right. We aren't retraining anything.
Yeah.
So how can changing the prompt string magically make the underlying math engine smarter? It feels like superstition.
Well, it doesn't make the engine smarter, exactly. It changes the trajectory of the calculation through the model's layers. Yeah, think of it like this. When you append, let's think step by step, you are essentially forcing the probability distribution into a completely different region of the latent space.
Oh, interesting. So you're steering it.
Exactly. You are steering the attention mechanisms away from immediate reflexive recall and toward a region of the training data that is dominated by procedural logic.
Because it's trying to predict the next token.
Right. The model is just predicting the next token. And the tokens that usually follow the phrase, let's think step by step in the training data are structurally constrained to be, sequential logical steps.
So we are essentially hijacking the model's pattern recognition.
That is exactly what it is.
Because its training data is full of textbooks, Stack Overflow threads, math forums where people break down problems sequentially. So those 5 words act as a homing beacon for that specific structural pattern.
A homing beacon is a great way to put it. And, if you want to tighten that structural constraint even further, you move past the zero-shot approach.
Right, into few-shot chain of thought.
Yes. Few-shot COT. This is where you, as the developer, actually provide worked examples in the prompt itself before passing the final variable.
Like giving it a template.
Precisely. You feed it a sample problem, and then you explicitly map out the intermediate reasoning steps that lead to the correct answer. You are defining the exact syntax.
Which, for a software engineer listener, is functionally in-context learning.
Yeah, absolutely.
We aren't just saying, take your time and think it through, which is kind of what zero-shot feels like. We're defining the latent space boundaries ourselves.
You are giving it the map.
Yeah. We are establishing this rigid syntactic template for the attention heads to latch onto. You give it the exact JSON structure or like the specific pseudocode pattern you want the intermediate steps to follow.
And that structure is crucial because it provides a deterministic pathway. But the true mechanical power of chain of thought, the reason it actually improves accuracy on complex tasks, goes way deeper than just adopting a logical tone.
Okay, so what is happening under the hood then?
We have to look at the architectural bottleneck of a transformer model.
Right.
If you pass a complex multi-step problem to an LLM without COT, you are demanding that the model map a highly complex input to a final correct output vector in a single forward pass through its layers.
Wait. It has to condense the entire calculation into a single token generation step.
Yes, which is mathematically brutal.
I can imagine.
It forces this massive logical tree to just collapse into one pass. And unless the specific answer was heavily represented in its pre-training data, the model simply lacks the computational depth in that single pass to calculate novel, multi-layered dependencies.
So it's basically forced to guess.
Exactly. It's going to hallucinate a leap of logic because it literally ran out of processing room.
Wow.
But, and here is the key, by forcing the model to output intermediate tokens using chain of thought, you fundamentally change the compute dynamic.
Yeah.
Every single output token requires the model to run a full cycle of its neural network.
Oh, wait, so generating tokens is quite literally buying the model more processing cycles.
Yeah.
We are turning text generation into compute time. That is wild.
Mechanically speaking, the tokens are the physical gears of the computation.
Okay, walk me through that. How do the gears turn?
So as each intermediate token is generated, it gets appended to the context window, right?
Right.
This means it is mathematically represented in the KV cache, the key value cache that the attention heads read from.
Okay, I'm with you.
So when the model generates the next token, its attention mechanisms can cross-reference those specific intermediate mathematical weights. It doesn't have to hold a nebulous concept across a single deep pass anymore.
It is writing state to its working memory.
That is exactly what it is doing.
That reframes the entire concept of a context window for me. It's not just a place to dump input documents for RAG or whatever. It's the artificial working memory required to avoid a cognitive buffer overflow.
Cognitive buffer overflow. I like that.
Well, it's exactly why we write pseudocode, right? Like when you are tackling a dense algorithmic challenge, if you try to write the perfectly optimized syntax for a recursive function in your head before touching the keyboard, you are going to drop a variable.
For sure, every time.
Your biological working memory overflows. But when you write out the pseudocode, you are offloading that cognitive burden onto the screen. So you can look at step 1 while calculating step 2.
And the LLM is doing the exact same thing with its KV cache.
That makes perfect sense.
By generating those stepping stone tokens, it pushes the intermediate calculations into an externalized state. So when it finally reaches the point of generating the ultimate answer, the attention heads have all that newly generated, highly structured context to draw from.
The intermediate tokens act as anchors for the final calculation.
Exactly.
But, okay, hang on. If tokens equal compute, and compute equals server costs and latency,
Yeah, I see where you're going with this.
we are suddenly looking at a massive API bill and huge latency spikes just to get an AI to, quote-unquote, think.
Yes, you are.
So for an engineering team building at scale, what is the actual ROI here? Like, when do we swallow that compute cost?
Well, the engineering trade-off is stark. You absolutely do not use chain of thought indiscriminately. The heuristic outlined in the source notes is very clear on this. COTI is designed for multi-step problems.
Multi-step only.
Right. Complex math, layered logic puzzles, and multi-stage planning tasks. Basically, tasks where the answer relies on a sequence of dependent variables. If step 3 requires the output of step 2, you need the intermediate tokens to act as those KV cache stepping stones.
Right. But for simple tasks, it's an anti-pattern.
100%.
Like if you are building a routing layer for customer support tickets and you just need the AI to tag an email as angry, happy, or confused, using chain of thought there is just architectural malpractice.
It really is. You are introducing latency for absolutely no reason.
And you're burning tokens.
And worse than burning tokens, you are degrading the user experience. If a user is waiting for a simple sentiment tag or a Boolean flag, they do not want a 3-second delay while the model writes a paragraph about why the user sounds frustrated.
Yeah, nobody wants to read an essay about an angry email.
Exactly. For single-step classification, the model's raw pattern matching capability in a single forward pass is already optimized. The deep layers converge on sentiment classification almost instantly.
So in a modern microservice architecture, you would route the single-step classification tasks to a smaller, faster model without QT.
Yes. Keep it lean.
And then you reserve chain of thought for the complex autonomous agents. Say, an agent responsible for planning multi-server deployment logic.
It's the perfect example.
Something where it has to check dependencies, sequence database migrations, and handle rollback states.
Right, because in that deployment scenario, if you asked it to output the final bash script without showing its work, it doesn't have the compute cycles to map out the dependency tree.
It's just going to guess.
It will guess what a plausible final script looks like based on latent space averages, and it will probably hallucinate a dependency. The rule of thumb for developers evaluating a task is pretty simple.
That's the rule.
If a human needs a whiteboard to map out the dependencies, the LLM needs chain of thought to populate its KV cache.
Okay, I love that.
But if a human can categorize it in a split second on instinct, the LLM can do it zero shot without suti.
The whiteboard heuristic is great, but applying that logic brings us to a part of the source material that kind of fundamentally challenges how we evaluate these systems.
Oh, yeah. This is where it gets weird.
Yeah, because we know CoT improves accuracy for those whiteboard-level tasks. We know generating intermediate tokens buys the model the compute cycles it needs. But there is a massive disconnect between the text the model outputs and the vector math happening under the hood.
The faithfulness problem.
Exactly. The nodes call it the faithfulness problem. And it is fascinating.
It really is. This is the frontier of AI interpretability, and it's where the mechanical reality of LLMs gets incredibly opaque.
Right. Because when we see a model output a beautifully structured chain of reasoning like step 1, step 2, step 3, culminating in the correct answer, our human instinct is to assume causality.
We want to believe it.
Yeah. We assume the model actually used the semantic meaning of step 1 to compute step 2. We assume the text it prints is a faithful log of its internal processing.
But the faithfulness problem suggests it's not a log at all. It might just be a post-hoc rationalization. The model is predicting the syntax of logic, but the actual vector calculations finding the correct answer might bypass those semantic steps entirely in the deeper layers of the neural net.
That is just wild to think about.
We have to remember how these models are trained. They are optimized to generate human-readable text that looks like the training data.
They are massive autocomplete engines.
Exactly. If you prompt it to explain its reasoning, the attention mechanisms are heavily weighted to predict tokens that form a plausible-sounding explanation.
Right. Plausible being the key word.
Yes. It is entirely possible, and research heavily suggests this is often the case, that the deep layers of the network converge on the correct conceptual answer almost immediately through vast, high-dimensional pattern recognition.
Meaning the reasoning we read is just the model backfilling the text to satisfy the prompt's structural constraint.
Yeah, it's just filling in the blanks.
It's the CEO boardroom justification.
Wait, I like this. Explain that.
Okay, so think about a CEO making a massive decision to acquire a startup. The actual decision is made based on like 30 years of subconscious industry pattern recognition, a gut feeling, and maybe a little ego.
Oh, absolutely. It happens all the time.
But they can't present gut feeling to the board of directors.
Yeah.
So they have an analyst generate a 50-slide deck of financial projections, market synergy, and strategic alignment.
Right.
The logical justification is entirely fabricated after the decision has already been made, purely to make it palatable for the board.
That is a brilliant analogy, and the LLM is acting as both the CEO and the analyst. The intermediate tokens are structurally necessary, like we said. They do buy the model, the computational time and space, and the KV cache to stabilize that final answer.
It still needs the tokens to think.
Yes. But the semantic meaning of those tokens, the actual English words we are reading on the screen, might just be the slide deck.
It's just the presentation layer.
Right. The underlying vector transformations that actually solve the multi-step math problem might not map to the English words, therefore, we carry the two.
So the stepping stones of compute are real, but the paint on the stepping stones is an illusion.
That is a great way to summarize it.
Which, for a software engineer used to deterministic systems, where a stack trace tells you the exact line of code that triggered a null pointer exception, this requires a complete paradigm shift.
A huge shift. You can't just read the logs and trust them.
Right. We are dealing with systems that are functionally highly reliable, but fundamentally opaque. We can verify the final output, but the internal logging, the chain of thought, is, well, a creative fiction.
It forces developers to treat LLMs less like traditional software functions and more like complex natural phenomena.
Like studying the weather.
Kind of, yeah. You can observe the inputs, you can measure the outputs, you can alter the environment by using CoT to provide more compute time, but you cannot fully trust the system's own explanation of its internal state.
Which means we have to design our application architectures around verification, not just trust.
Absolutely. Trust but verify. Well, mostly just verify.
Right. If the model outputs a deployment script using chain of thought, we don't trust the script just because the reasoning steps look sound and logical.
Never deploy untested LLM code.
Right. We pipe that script into a sandbox environment and test the execution. We use the code T to get a better result, but we completely decouple the semantic explanation from our validation pipeline.
And that architectural mindset perfectly sets the stage for the next module in these source notes.
Oh, right, because we aren't done yet.
No, because once you understand that chain of thought gives the model an internal whiteboard to process complex dependencies, the next logical step is giving it the ability to verify its own work against external reality.
You're talking about React prompting.
Yes, REACT, which stands for reason and act.
Right.
It's what happens when you combine this exact step-by-step reasoning with actual tools.
Like API calls.
Exactly. The model says, let's think step by step. First, I need to check the current database schema. But instead of hallucinating the schema based on its latent space, it actually executes a SQL query.
Oh, wow.
Yeah, it reads the live result into its context window and then continues its chain of thought based on real data.
So it bridges the gap between the internal, potentially hallucinated reasoning and deterministic real-world state.
Exactly. It's giving the AI a pair of hands to go along with its whiteboard.
That is incredibly powerful. We will definitely be digging into the mechanics of React prompting next time we dive into these nodes.
For sure. There is a lot to unpack there.
But, as you turn your attention back to your IDE and you stare down your next massive API integration, I want to leave you with a lingering question about that faithfulness problem we just talked about.
It's a tough one to shake.
It really is. I mean, we know the intermediate tokens in a chain of thought prompt are mathematically necessary to buy the model processing time. We know they reliably lead to a more accurate final answer.
The math checks out.
But if the semantic explanation the model prints out is essentially a post-hoc rationalization, a slide deck justifying a high-dimensional vector calculation, does it actually matter that it's a hallucination?
That is the big question.
Right. If the final code the AI generates compiles perfectly, runs efficiently, and solves your algorithmic bottleneck without a single bug, should we care if the AI's comments explaining its logic are just a polite fiction?